Hello everyone, I'm going to introduce a work focused on fibrosis staging from liver pathology images. First, I'll introduce a background motivation. Non-alcoholic fatty liver disease is the most common liver disease, which affects around 30% of the population. This high prevalence places a significant diagnosis burden on the current medical system. Liver biopsy image is a gold standard for diagnosis because it provides cell-level structures. During the examination on whole slide image, fibrosis staging is a key factor. Here is a figure illustrating the concept of fibrosis. Given a liver biopsy image, the fibrosis stage ranges from 0 to 4. Fibrosis detection relies on the location of fibers and vessels. Fibrosis 0 refers to the no fibers around vessels. Then fibrosis begins with fiber deposition around vessels. While fiber accumulate, they expand and connect vessels at different strengths. Finally, the fibers form a bridge. The relationship between vessels and fibers highlights the inherent advantage of representing image with graph. The information is crucial for grading the stage of fibrosis. In summary, fibrosis exhibits graph-like pattern. However, current graph-based method may not be applicable to fibrosis staging. For example, considering two figures, one showing fiber between vessels and the other without fibers, we can represent graph node located at vessel. The red line connecting the graph nodes represents the graph edge. The graph edge reflects the connectivity caused by fiber deposition, depicted with varying thickness. However, ordinary graphs tend to learn node feature representing as a single object. Then a new graph structure representation is required. Our basic idea is to represent the image with a primordial graph, which can model two tissue structures at the same time. Specifically, given a liver biopsy image, we can build a graph where the node represents the location of vessels. The graph is referred to as a primal graph. Then we can do a primordial graph transformation, where the original graph edge is transformed as graph node in the dual graph. Here is our proposed method. Given a whole cell image, it is first processed through a vessel fiber segmentation module. Then, image tails containing fiber or vessels region are tracked for further processing. For each image tail, based on the segmentation of vessels and fiber, we can derive the key points, which include the location of vessels and the ends of the fiber extension. Using these key points, we can construct a primordial graph. The associated node embedding consists of textual feature from the image encoder or position feature. The primordial graph is then fed into a primordial graph convolution module for node feature learning. Tail-level features are pulled from all graph embeddings, and these tail-level features are then pulled together to generate whole cell-level features for final fibrosis staging. Here, we further demonstrate the graph building procedure. Given the whole slide image, we will first identify the fiber and vessel regions, rendering in purple and white. When deriving key points from these segments, the key points are located at vessels around the fibers. The primal graph is built from these key points. Then, the dual graph is then obtained from transforming the graph edge into nodes. Here is a figure showing the feature embedding of the subgraph. Each dot refers to a subgraph. The cluster label is generated by a k-means clustering algorithm. We can see that model is able to distinguish different graph structure representation based on the spatial shape. Here we further demonstrate the distribution of the importance score when model make decision. We can see that the proposed method indeed learn to focus on the fibrous region. Finally, I will make a simple conclusion. We propose the interpretable method to explicitly learning the relationship between vessels and fibers. We convert a liver biopsy image into a collection of primordial graph and introduce primordial graph convolution network for fibrosis staging. Thank you.